In this video, we're going to talk about the polarity of the bond, the electronegativity, and eventually the overall polarity of the molecules, especially the covalent compounds. So to refresh our memories, let's go back and talk about the covalent bond. The covalent bond involves the sharing of electrons. So I'll have two atoms and there are going to be the electrons shared between those two atoms, and that's going to be the foundation for the covalent bond. Let me take in a very simple example where I have the H2 molecule. Now, when I draw the Lewis dot structure for the hydrogen, I'll have two electrons right in the middle of those two hydrogen atoms, and a better way for representing that would be a bond between the two hydrogen atoms. But instead of representing it as a bond, it's we want to actually look at the first representation where we can easily understand the bond polarity. Now, right now, this electron pair that's between the two hydrogens is actually being shared by both of those two hydrogens. So another way of saying, both of those hydrogens have the equal right toward those shared electrons. But then the question comes in, how do we really know that the shared electron stays right in the middle of those two atoms? Well, why not toward the left atom or why not toward the right atom? And that answer is given by the electronegativity. So the definition of an electronegativity is the affinity of an atom toward the shared electron in a covalent compound or a covalent bond. Okay, so in case of hydrogen, there is no both of the hydrogens has the same affinity for those electron pairs, and as a result, this this electron pair stays right in the middle of the hydrogen atoms. But let me take another example where the electronegativity is actually different between the atoms. So I'll have HCl. All right, if I draw the Lewis dot structure for HCl, it's gonna look like this. So if you have hard time writing the Lewis dot structures, you may want to watch the other video where I have talked about drawing the Lewis dot structures in detail. So let's assume you go ahead and wrote down the Lewis dot structure for HCl, and you can clearly see this electron pair right now I have drawn right in the middle of the chlorine and the hydrogen. Okay, but then the question is, does this electron pair really stays in right in the middle? And the answer is given by the electronegativities. And right now we know the electronegativity of the chlorine is bigger than the hydrogen. Well, we haven't really talked about the trend, so just assume for momentarily that the electronegativity of the chlorine is actually bigger than the hydrogen. And if that's the case, this electron pair that's being shared is actually going to be closer to the chlorine. So it's not going to be closer to the hydrogen or in the middle, but rather it's going to be closer to the chlorine. And you can say chlorine has more access to that electron pair than the hydrogen. Now, when you do so, this chlorine actually gets a partial negative charge, and this hydrogen gets a partial positive charge. This delta sign right there, this looks like S, but it's called a delta. It means a partial sign on it. And if you recall, if an atom gains an electron, it gets a negative charge. But in this particular case, chlorine is actually trying to gain the electrons. It hasn't fully gained the electron. So it doesn't get a full negative charge, but it gets a partial negative charge instead. And the same story with the hydrogen. If an atom loses electron, it gets a full positive charge. But here, hydrogen is losing the access to those shared electrons, so it's getting a partial positive charge, not a full negative, not a full positive charge. Now, once you have figured out which one is going to be your partial positive, and which one is going to be partial negative, you can always draw in a dipole that looks like this. So yeah, the dipole always starts from the positive end and goes to the negative end with the help of an arrow. So this is going to be your dipole moment for this particular bond right there. And you will see in the dipole moment only if the bond is going to have a difference in the electronegativities, or another way of saying you'll have a polar bond when we go back to the hydrogen, since both of those hydrogens has the same electronegativity values, there is no dipole moment, so there's no dipole in there. And as a result, this bond is going to be nonpolar. Okay, so your first task after learning the electronegativity is be able to identify if you have a polar bond or a nonpolar bond. So when I redraw this chlorine or HCl, I don't really have to draw the bonds, the electrons in between. I can still draw in the form of the bond like this, but now I know the chlorine is more electronegative than the hydrogen, so the electron pair will be more toward the chlorine. So this chlorine will have a negative charge, and this hydrogen will have a partial positive charge. And as a result, you're going to have a dipole moment going from the hydrogen to the chlorine. Okay, so how do we know the chlorine actually has a higher electronegativity value than the hydrogen? Well, there is a trend of the electronegativity in the periodic table, and this is something you guys want to memorize for right now. So when you're looking at the period from left to right, your size decreases. If the size is decreased, all right, then your electrons, or the shared electrons in that case, is going to be closer to the nucleus, so they're going to have a stronger pull for those electrons. So as a result, your electronegativity is going to increase. Okay, so you can say when we go from left to right, like in this scenario, your En is going to increase. However, I do want to mention the electronegativity of these noble gases is actually zero. So whenever you look at noble gases, the electronegativity of these noble gases is going to be zero. Their electronegativity is even actually less than the electronegativity of the metals. Okay, let's go back to what happens down the group from top to bottom. When you're going from top to bottom, your size increases. If your size is increasing, your nucleus is getting further away from the valence shell, so they're going to have a weaker pull for those electrons that are being shared. So as a result, your electronegativity decreases. So when you go down the group, your electronegativity is going to decrease. So En values will decrease. Okay, so if you have two atoms where, let's say, the A and B, and if the electronegativity difference, so I'll say En difference between the two atoms is actually less than 0.5, then you take those as nonpolar bond. All right, if their difference is actually bigger than 5, so the difference in, I'll just write that down, like the delta En, so the change in electronegativities between the two atoms is bigger than 0.5, then it's going to be polar covalent compound or bond. All right, and if you're making a bond between the metals and the non-metals, then that's going to be an ionic bond. All right, so we're not really talking about ionic bonds. We're only talking about the bonds that are going to be between the non-metals only, because that's what the covalent compounds are. So keep in mind, if your electronegativity difference is less than 5, it's going to be nonpolar bond, and if your electronegativity difference is bigger than 0.5, it's going to be polar covalent polar covalent bond. However, you may not be given these values. If you're given these values, then you can certainly calculate it, but for the most part, you're not going to be given those values, so you have to rely on this electronegativity trend that we just learned. So no, electronegativity increases when you go from left to right, and no, the noble gases have zero electronegativity, and as you go from top to bottom, the electronegativity decreases. So let's talk about these bonds right there. So we just mentioned about the nonpolar covalent bonds, so there is not going to be any dipole moment. So you can use the values to figure out the polarity of the bond, whether it's going to be nonpolar or polar, if you're given the values. But if you're not given the values, then you can just look at the electronegativity trend in the periodic table. You will not have any dipole moment when you're making the bond between the same atoms. Like, for example, we talked about hydrogen. So the hydrogen-hydrogen bond is going to be nonpolar because both hydrogens will have the same electronegativity. Or Cl2, it's going to be nonpolar. And talk about O2, that's going to be nonpolar. Or I can say Br2, that's going to be nonpolar. So if you see a bond that's made between the same atoms, or I can say a carbon-carbon bond is also going to be nonpolar. All right, so what about a bond that's not between the same atoms and that's still going to be considered a nonpolar? There are some bonds that you have to really worry about, but the most important one that's going to be between the heteroatoms and still considered nonpolar, it's going to be a carbon-hydrogen bond. If I look in the electronegativity trend, if I go back, well, you may want to ask yourself here, who's more electronegative out of hydrogen and chlorine, hydrogen and carbon? Well, you can clearly see your carbon is actually onto the right side in the periodic table than the hydrogen. So carbon is indeed more electronegative than your hydrogen. However, the electronegativity difference is not big enough to create the polarity in the bond. So another way of saying the electronegativity difference, so delta En, in this particular case is actually going to be less than 0.5. So you don't have to memorize that, but just memorize that your carbon-hydrogen bond anytime you see is going to be considered a nonpolar. Okay, and there are going to be some other bonds like boron-hydrogen bond is also nonpolar, but boron is in a metalloid. Here we're going to be focusing mostly on the non-metal bond. All right, so another way of saying covalent compounds only. Okay, so carbon-hydrogen kind of does go a long way, especially when you take organic as well. All right, let's talk about polar bonds. If you see a bond between any other non-metals, consider that to be polar. All right, that's going to have a net dipole moment there. So if I have, let's say, a carbon-chlorine bond, assume, or I have maybe an oxygen-hydrogen bond, and I'll draw the dipoles on those in a minute. And then let's assume I have a hydrogen-fluorine bond, and let's figure out what the dipole is going to be on those. You don't necessarily have to memorize their electronegativity values. Just by the periodic trend of electronegativities, know that these bonds are going to be polar. Now, between the carbon and chlorine, what do you guys think who's going to be more electronegative? So if I go back in the periodic table here, figure out where your carbon is and your chlorine is. Your carbon is right there, 6, and your chlorine is an halogen. So chlorine being more onto the right side, it's going to be more electronegative than the carbon. So since your chlorine is more electronegative, I would say chlorine would have a partial negative charge. So it's going to have a partial negative charge, and carbon is going to have a partial positive charge. So I will have an net dipole there going to the right side here. Okay, so this is how you're going to be drawing your dipole there. Okay, what about oxygen and hydrogen? Well, oxygen is onto the right side of the periodic table and hydrogen is way onto the left side of the periodic table. So as a result, hydrogen is less electronegative than the oxygen. And since oxygen is more electronegative, it will have a partial negative charge on itself and hydrogen will have a partial positive charge on itself. So when I draw the dipole on that particular one, it's going to be looking like this. All right, so it starts from the hydrogen and goes to the oxygen. So you want to make sure you're able to draw the dipoles on those molecules. And then what about the HF? Well, the same story here. Hydrogen is way onto the left side of the periodic table and fluorine is onto the right side. Fluorine, being more electronegative, is going to have a partial negative charge and hydrogen is going to have a partial positive charge. Okay, so when I draw the dipole, it's going to be going from the hydrogen to the fluorine, just like that. Okay, so this is how you're going to be drawing the dipoles based on the electronegativity trend in the periodic table. So don't memorize those values, just know these trends and you can draw the dipoles based on that. Okay, so once you know your bonds, whether it's polar or nonpolar, you can determine the overall polarity of the molecule. All right, so let's figure out how you're going to be using the knowledge of the polarity of the bond to determine the polarity of the molecule. So case one, if the molecule has only non-polar bonds, that means there's no net dipole, then your overall molecule is going to be nonpolar. So I will say here, overall polarity of the molecule is going to be nonpolar. So that's just a dead giveaway. If you figure out the polarity of the bonds, no polarity of the bonds, there's not going to be net dipole. That's going to be overall nonpolar. And I can take an examples of maybe CH4. So in CH4, when you draw the Lewis star structure, this is how it looks like. And we know, I don't really have to draw the dipoles here because we know carbon and hydrogen bonds are considered to be nonpolar. So if those bonds are nonpolar, your overall molecule is also going to be nonpolar. So all your hydrocarbons are actually nonpolar. I can write down maybe C2H6, or I can write down octane, which is like C8H18. That's also nonpolar, because the only type of bond you will have in those is going to be either a carbon-carbon bond or a carbon-hydrogen bond, and both of them are going to be nonpolar. So that's going to be your case one, and that's something, the very first thing you want to look for. Okay, so then what about if the molecule actually has polar bonds? All right, so let's look at that example. If the molecule has polar bond, that does not necessarily mean your overall molecule is going to be polar or nonpolar. All right, you have to look at something else beside that. There's two options when you have polar bonds in the molecule. If the given molecule has a planes of symmetry, or another way of saying the molecule is symmetrical all around, then there is not going to be any net dipole, and overall the molecule going to be nonpolar. So overall polarity in that case is going to be nonpolar. And I'll give you an example in a minute. And that happens a lot of time. Let's take an example of maybe CO2. You may want to pause the session here and draw the Lewis star structure and predict the shape using the Vesper theory of CO2, because that's extremely important to determine these polarities here. So let's say you go ahead and do that and you figured out, okay, the CO2 is going to look like this. Okay, so you got, we do have a carbon-oxygen bond here, and what do we know about the carbon-oxygen bond? Well, oxygen is actually more electronegative than the carbon, so as a result, both of these oxygens are going to have a partial negative charge, and carbon is going to have a partial positive charge. So what that means, there isn't a dipole going from the center to the right, and there isn't a dipole going from the center to the left. Well, both of those dipoles are being created by the same atom. As a result, they cancel out, so there is no net dipole. All right, and another way of saying this molecule is actually symmetrical. So when we look at the symmetry, you want to actually kind of draw a vertical line, and then you can see how the left side and the right side is the same. And then you can also draw a horizontal line, and you can see the top side and the bottom side is the same. So you can check either way, but looking at having the net dipole or not having the net dipole is the best way to determine the polarity of the molecule. But then obviously that also comes from the planes of symmetry. Let me take another example. What if I have CCl4? Okay, so pause the session here and go ahead and draw the Lewis star structure of CCl4, and this is how it's going to look like. All right, so now if I draw the three-dimensional form of that, it's going to be carbon, and then I got two bonds coming out of the page, one bond coming out of the page, one bond going back into the page, and the two bonds going to be in the plane. So just something like that. So either way you want to draw, that's fine, but if you're just drawing it two-dimensionally, you can just draw the first way we have drawn here. Now, based on the electronegativity values, you know chlorine is going to be more electronegative than the carbon because it's more onto the right side. So each of these chlorine is going to have a partial negative charge and carbon as a result is going to have a partial positive charge. So since carbon is going to have a partial positive charge, I can draw all these dipoles from the center to the left to the right, and then from the center to the top. Maybe I'm going to use a different color there. So I have a dipole going to the top, and then I got a dipole that's going to the bottom here. So you can clearly see how the left dipole cancels the right dipole and how the top dipole cancels the bottom dipole. So even though having the polar bonds, overall there is no net dipole. So I can go ahead and write down there overall no net dipole. And this is going to be nonpolar at the end of the day. And then you can clearly see the symmetry of the molecule here. If I draw, let me change the color here. If I draw a couple of lines here, if I draw a line vertically, like this red line here, you can see the right side and the left side of the molecule is the same. And then if I can draw another line that goes from, let's say from the horizontal line, then you can see the top of the molecule is the same as the bottom of the molecule. So that's when symmetry means. If your molecule is symmetrical, means it's not going to have any net dipole at the end of the day, even though you have polar bonds. So sometimes they just ask you those questions. Can you have polar bonds and overall molecule to be nonpolar? Yes, you can. Anytime you have a symmetrical molecule or anytime all the dipoles cancels out, you could still have polar bonds, but overall your molecule is nonpolar. Okay, then what about the second option? When you have polar bonds, but the molecule does not have a plane of symmetry, so in that case you will have a net dipole and the molecule is going to be considered polar overall. Now let me take a few examples here. Let's say water. So maybe draw the Lewis-Strauss structure of water and predict the geometry of the water. When you draw the Lewis-Strauss structure and use the Vesper theory to predict the shape of the water, it's going to come out to be bent. So make sure you know how to draw these. And if you have a hard time drawing those, you may want to watch my other lesson where I have talked about drawing Lewis-Strauss structures in details. So this is how it's going to look like. And now you can clearly see there is no symmetry in the molecule. I mean, you can momentarily argue that if I draw a vertical line here, then the left side and the right side is the same. But what about when you draw a horizontal line? Like let's say you draw a horizontal line here, then there is the top of the molecule is not the same as the bottom of the molecule, so that's why it does not have a plane of symmetry. So let me just go ahead and redraw that and draw the dipoles on those. So you can clearly see oxygen is going to be more electronegative than those hydrogens, so I can have a partial negative charge on the oxygen and partial positive charges on the hydrogens. So I would have this electron, the dipoles going this way from the bottom to the top at an angle. So they're not really canceling one another out. So if I maybe just move this a little bit. So since they're not canceling one another out, you will still have a net dipole going up there. So that's going to be the direction of your net dipole in the molecule. So since you have a net dipole in the molecule, it's going to be overall polar. Okay, well, let me take another example. What if I have something like CHCl3? It's also called chloroform. So when I draw the Lewis-Strauss structure of CHCl3, so you may want to pause the session and draw that before you move on. This is how it's going to look like. Now I know the carbon-chlorine bond is going to be polar, so I can clearly say there is going to be a dipole moment going from carbon to the chlorines. So you can see the left dipole, right dipole, they may cancel one another out. But then you do have a bottom that's dipole that's going to the top. But then this carbon-hydrogen bond is actually nonpolar. So this bond is nonpolar. And since that bond is nonpolar, you don't have anything to balance out this dipole that you have created between the top chlorine and the carbon. So since that creates an asymmetry in the molecule, that gives a net dipole in the molecule. So that gives um, a net dipole. All right, so that's why this molecule overall is going to be polar. All right, and I can look that in the form of a symmetry. I can, if I redraw this, okay, so let's assume I have the electrons there as well. If I draw a line, vertical line, I can clearly see my left side and the right side is the same, so it's symmetrical along that way. But what about if I draw a horizontal line, then the top and the bottom is not the same, all right? So they're not the mirror images of one another. So you can see this molecule is asymmetric in that case. So if you have asymmetric molecule having at least one polar bond, that gives the molecule overall polarity. All right, so hopefully this video was helpful. Make sure you are able to learn to determine the polarity of the bond before you can look up the overall polarity of the molecule. And I'll have some more examples posted. And if you have any questions about any of these slides, please leave the comments in the section.